Humanity's journey into space is a testament to our thirst for exploration. From the first tentative steps on the moon to the ongoing endeavor aboard the International Space Station, we have continuously pushed the boundaries of how long we can live and work beyond Earth. The current record for the longest continuous time spent in space belongs to Russian cosmonaut Valery Polyakov, who completed a remarkable 437-day mission aboard the Mir space station. This incredible feat, along with other long-duration missions, provides invaluable data on the effects of prolonged spaceflight on the human body and mind. These missions serve as stepping stones, paving the way for even more ambitious journeys to Mars and beyond. As we venture further into the cosmic ocean, understanding the challenges and developing effective countermeasures becomes crucial for the future of human space exploration. Space is a profoundly alien environment, vastly different from the comfortable cradle of Earth. The absence of gravity, exposure to harmful radiation, and the confined living conditions all pose significant challenges to human physiology. Our bodies, finely tuned for life on Earth, must adapt to this new reality. Understanding these adaptations and the limits of human resilience is paramount to ensuring astronaut health and mission success on long-duration space flights. One of the most immediate and noticeable effects of spaceflight is space adaptation syndrome, often referred to as space sickness. This condition, caused by the disorienting effect of microgravity on the inner ear, leads to nausea, vomiting, and dizziness. While most astronauts acclimate within a few days, understanding and mitigating space sickness remains important, especially considering the potential disorientation during critical mission phases. In the weightless environment of space, our muscles and bones face a unique challenge. Without gravity, muscles atrophy and bone density decreases. This weakening is a significant concern for long missions. Astronauts exercise 2 hours daily with specialized equipment. Resistance training helps maintain muscle mass. Treadmills and bikes preserve bone density. These measures ensure astronauts stay strong for spacewalks and return to Earth safely. Beyond the physiological challenges of microgravity, space presents another, more insidious threat: radiation. Unlike Earth, which is shielded by its magnetic field and atmosphere, space is awash with high-energy particles from the Sun and distant cosmic rays. Prolonged exposure to this radiation can damage DNA, increasing the risk of cancer, cataracts, and other health problems. Protecting astronauts from radiation is a complex challenge. Spacecraft shielding can block some radiation, but for long-duration missions, especially those beyond Earth's protective magnetosphere, additional measures are required. Researchers are actively developing advanced shielding materials and investigating pharmaceutical countermeasures to mitigate the harmful effects of space radiation. Understanding and minimizing radiation exposure is paramount to ensuring the long-term health and safety of astronauts on future deep space missions. Section 5. The Mind in Space. Psychological challenges of long-duration missions. While the physical challenges of spaceflight are substantial, the psychological impact of prolonged isolation, confinement, and the demanding nature of space missions should not be underestimated. Astronauts are highly trained individuals, rigorously selected for their mental resilience and adaptability. However, the unique stressors of space travel can take a toll. Isolation from loved ones, the lack of natural light and open spaces, and the constant pressure of high-stakes missions can contribute to sleep disturbances, mood changes, and interpersonal conflicts. Recognizing the importance of mental well-being, space agencies prioritize psychological support for astronauts before, during, and after their missions. This includes providing opportunities for communication with family and loved ones, fostering team cohesion, and offering psychological counseling as needed. Section 6. Combating the challenges, countermeasures, and research for space survival. Addressing the multifaceted challenges of long-duration space flight requires a multidisciplinary approach, combining cutting-edge research with practical countermeasures. Scientists and engineers are constantly working to develop innovative solutions to mitigate the risks and enhance the well-being of astronauts on future missions. Artificial gravity, a concept often seen in science fiction, is being investigated as a potential solution to the problems caused by microgravity. Rotating habitats or spacecraft could generate centrifugal force, mimicking the effects of gravity and potentially mitigating muscle and bone loss. While still in the early stages of development, artificial gravity holds promise for future deep space missions. Section 7. Future Horizons, Artificial Gravity and Advanced Life Support Systems. Beyond artificial gravity, advancements in life support systems are crucial for enabling long-duration space travel. Current life support systems on the ISS rely on resupply missions from Earth. For missions to Mars and beyond, self-sustaining closed-loop systems are essential. These advanced systems would need to recycle air and water, process waste, and potentially even grow food, minimizing reliance on Earth. Research into bioregenerative life support systems, which utilize plants and algae for oxygen production and waste recycling, is ongoing. These systems, inspired by Earth's own ecosystems, hold the key to sustainable human presence in space. Section 8. Pushing the limits. Will we ever conquer time in space as we venture further into the cosmos? The question of how long humans can live in space remains a captivating and complex one. While technological advancements will undoubtedly extend our reach, the fundamental limits of human physiology may ultimately dictate our endurance. However, the spirit of exploration knows no bounds. The human drive to push boundaries, to seek new knowledge and frontiers, will continue to propel us forward. Whether we establish permanent outposts on Mars, venture to the icy moons of Jupiter and Saturn, or even journey to distant star systems, the quest to explore the universe will undoubtedly continue to shape our destiny. Section 9. Conclusion. The future of humanity among the stars. Humanity's foray into space is still in its early stages. As we learn to live and work in this unforgiving environment, we expand our understanding of the universe. The challenges of long-duration space flight are formidable, but innovation and the human drive to explore will lead to solutions. The knowledge we gain will enable us to venture further into the cosmos and have profound implications for life on Earth. The future of humanity is intertwined with our exploration of space.